the first talk of the session.
Yeah, Jamal.
Okay. Yes. Yeah, I think everything has been said, so I don't have anything to add. Just I would like to thank everybody who worked hard in this program, and so I thank Munindar for introducing me, and Mohan, who did Munindar mentioned a lot of work. So
Okay, so let me thank James, Carl, and J1C2 organizing committee again for the great effort of making this J1C2 track possible. And thank you all again. So now I can conclude this session. So Mohan, we can start the paper presentation session.
Okay. And it appears that our first speaker is here. So Zhao Haliang is here, I think.
Yes, I'm here.
Yeah. So are you going to, if you're going to share your screen, maybe either we can.
Okay.
Yeah. Okay, great. Works.
Hello, everyone. Welcome to my presentation. Currently, I'm a PhD student from Zhejiang University, and my name is Haliang Zhao. I'm going to talk about my TSA paper entitled Distributed Redundant Placement for Microservices-Based Applications at the Edge. As we can see in its title, scheduling is replaced by placement. This change is made during the page proofs, but it hasn't been updated on the IEEE webpage. In the first section, I will show how the service placement problem is motivated at the network edge. Then I'm going to describe our system model and problem formulation. The proposed algorithm and the experimental result will be mentioned briefly at the end. So let's begin with the first section, a brief introduction to multi-access edge computing. Today's mobile applications becoming more and more computation intensive, location aware and delay sensitive, which put a great pressure on a traditional cloud computing paradigm to guarantee the quality of service. To address this challenge, MEC was proposed to provide services and to perform computations at the network edge without time-consuming backbone transmission, so as to enable faster responses for mobile devices. MEC offers not only the development on the network architecture, but also the innovation in service patterns. Considering that the small-scale data centers can be deployed near cellular tower sets, there are existing possibilities that the microservice-based applications can be delivered to mobile devices without backbone transmission. If we can set up a unified service provision platform in the edge network. So the problem is how to perform service provisioning at the network, at the edge network. When we talk about service provisioning as the edge network, there are actually two main problems to deal with. The first problem is where to place the services. And the second problem is how to deploy the service instances. In this paper, we mainly address the first problem, since the second problem can be perfectly solved with Docker and lightweight Kubernetes, for example, the KuberEdge. In the last 2 years, there exists work studying the placement at the network edge from the perspective of quality of experience or the budget of applications service providers. However, those works commonly have two limitations. Firstly, the to-be-deployed service only be studied in an automatic way. It is often treated as a single abstract function with given input and output data size. Time series or compensation property of services are not fully taken into consideration. The second problem is high availability of deployed service is not carefully studied because the heterogeneity of the edge set, such as different CPU cycle frequency, different memory footprint, different background load, transient network interrupts, and many other problems, the service provisioning platform may face great slowdown or even runtime crash. To solve the problems in this paper, we propose a distributed redundant placement framework, SAARP. redundancy is the core of SARP, which allows that one microservice candidate to be dispatched to multiple edge sets. By creating multiple candidate instances, it boosts a faster response to service requests. With one candidate deployed on more than one edge set, requests from different end users at different locations can be balanced. Here is our typical scenario. Our motivation is built on the heterogeneous network. In this network, we have at least one macro base station, MBS, and several small cell base stations, SBS. Each small cell is co-located with a small scale server, which gives the processing capacity of small cells. The small cells are logically interconnected for message broadcasting and routing. The services considered in our paper is a service function chain. A service function chain is a chain of microservices. Each microservice has multiple candidates. For example, when we're shopping on the client browser, we firstly search the items we want, which can be realized by many set to search APIs. And secondly, we add them to the cart and pay for them. The payment can be accomplished by WeChat Pay, PayPal, Alipay by invoking their APIs. After that, we can review and rate for those purchased items. In this example, each microservice is focused on single business requirements. And we have a 4 microservice app here. We use M to represent a microservice, and we use C to represent a candidate. In this figure, microservice 1 has 2 candidates. In real world, we cannot know the preference of end users' service selection and composition. If we can take this uncertainty into our problem formulation, it will greatly increase the hardness of the problem. In our work, we use simple average approximation to approximate the expectations of service selection and composition. Will be talked later. This slide shows the redundant placement example. We can see that every microservice candidate has the possibility to be dispatched to any small cells, which greatly increase the hardness of the problem. In this example, the undirected connected graph of the edge network consists of 6 SBS. The number tagged inside each SBS is the maximum number of placeable candidates. For example, SBS2 can be placed at most 4 candidates. This constraint exists because the edge set have very limited computation and storage resources. Compared with the cloud data centers, the squares beside each SBS are the deployed candidates. For example, SBS1 deploys 2 candidates, C11 and C21. Because the redundancy mechanism, the same candidates can be deployed on multiple SBS. For example, C21 has been deployed on both SBS2 and SBS1. In this figure, we also have 2 mobile devices, MD1 and MD2. They are located beside SBS1 and SBS5. We use quality of service, the average service response time for each end user to guide the design of placement policies. In our design, every mobile device sends its service request to the nearest SBS to invoke their first microservice of its service function chain. For example, in this figure, MD1 sends its service demand to SBS1 to invoking his first microservice. For a mobile device, if no SBS accessible around, the response should be made by the MBS, and all the microservices are processed by cloud. If there are SBS available, but the request microservice is not deployed on the nearest SBS, then the request is processed on the SBS within the edge network with the shortest data transfer overhead. The shortest data transfer overhead is obtained by the shortest path algorithm in the edge network. In the last condition, the request microservices is not placed on any SBS in the heat net, then the request has to be processed on cloud. For the subsequent microservices, we have one principle. If the microservice has candidate instance deployed on the edge network, then process it within the network. Otherwise, we process it on the cloud. Our target is avoid backbone transformation so as we can minimize the average response time. A good service placement should spend as less time spent as possible. We need to find a service placement policy to minimize the response time. What we needed to determine not only the how many instances required for each candidate, but also which edge sets to place those to place these instances. Okay, I will show your system model briefly here because we have many formulations. For each mobile device, the response time is the adding result of 3 parts. The first part is the uplink transmission time. And the second is the execution time and the downlink transmission time of all microservices. And here we had some here because we have to add in all the results, all the queue results, because queue is the number of microservices. We need to calculate the sum of time spent on every microservice. And here this notation represented the C queues candidate of the queues microservices for the ICE mobile device. We have many notations here. The uplink and downlink transmission time of each microservice is decided by the multi-hop transfers in the connected graph of edge servers. For example, for the first microservice, we have to discuss 4 cases. The first is if the mobile device is not covered by any small cell, its request has to be processed by cloud through the MBS. That's the first case. The second case is the nearest SBS for the mobile device is not placed the requested microservice. In this case, the request still has to be processed by cloud. That's the second case. In both the two cases, the request is processed by cloud. The third case is the request
Everyone, it looks like we lost our speaker. Well, he's coming back. Good.
I'm sorry, I just have a network interruption here. I will continue. In this slide, we list all the discussions. We just skip the verbal formulations. And as we have mentioned before, our job is to find an optimal redundant placement policy to minimize the overall latency under the limited capacity of SBS. The heterogeneity of edge sets is directly obtained in the number is directly embodied in the number of can be deployed candidates. We can use BJ to denote this number for the J's SBS. BJ could be very different in the network because our edge network is heterogeneous. Our target is to minimize the overall response time on average. So the problem is how we solve it. In the first case, we use a framework named the simple average approximation. We use this simple average approximation to approximate the expectation of end user's service selection. The procedure is required because we don't know the user's service selection preference. The essential of simple average approximation is actually Monte Carlo sampling. Firstly, we need to select the sample size R and R prime here. As the sample size R increases, the optimal solution of the SAA problem, we call it problem 2, P2, converges to the true problem defined in the slide number 16. The problem P1, as we have defined earlier. However, the computation complexity for solving the P2 increases at least linearly in the same size R. Therefore, when we choose R, the trade-off between the quality of the optimality and the computation effort should be taken into account. R prime here is to use an optimal estimate of P1 with the optimal solution of P2. To obtain an accurate estimate, we have a reason to choose a relatively large sample size, R prime. We replicate generating and solving P2 with L-dependent and identically distributed replications. From step 4 to step 8, we call the algorithm guess to obtain the near optimal solution of P2 and recall the best so far result. From step 10 to step 13, we estimate the true value of P1 for each replication. After that, those estimates are compared with the average of those optimal solutions of P2. If the maximum gap is smaller than tolerance, then the algorithm stops and return the best solution. Otherwise, we just increase R and R prime and drill again. Within the SA framework, we design a genetic algorithm-based algorithm named GASS, guess, to optimize the instance placement decisions. Firstly, we initialize some parameters, for example, the population size, the number of iterations, and probability of crossover and mutation. After that, we randomly generate the initial population from domain X. From step 6 to step 10, guess executes the crossover operation. At the beginning of this crossover operation, guess checks whether crossover needs to be executed. If yes, it chooses the best 2 chromosomes according to their fitness values. With that, the later part of XP1 and XP2 are exchanged since the position of XPJ. From step 11 to step 13, guess executes the mutation operation. At the beginning of this mutation operation, it checks whether each chromosome can mutate according to their mutation probability. At the end, only the chromosome with the best fitness is returned. More details about the variable encoding can be obtained from our paper directly. Just skip the details here. The difficulty lies in the calculation of the response time under different cases, as we have, as I have shown you before, the verbose formulations. Let me show you the experimental results briefly. Our method is compared with several representative baselines and the state-of-the-art algorithm, GenDoc. The baselines are performed in 2 scenarios. In the first scenario, redundancy is not allowed. Each candidate can only be dispatched to only one SBS. It is used to evaluate the performance of redundant placement. In the second scenario, redundancy is allowed. It is used to evaluate the optimality of guess. From the left figure, we can see that guess outperforms the other algorithms in the overall response time. The right figure shows the response time achieved by each algorithm under different settings of service capacity. That's BJ. we can see that the GET still achieves the smallest response time. Now we can make a conclusion. In this paper, we study a redundant placement policy for the placement of microservice-based applications at the distributed edge. We firstly demonstrate a typical edge network, and we explore the possibilities of the deployment of composite microservices with container and Kubernetes. After that, we model the redundant placement problem as a stochastic optimization problem. For the application with composite and correlated microservices, we design the SAA-based framework and the GA-based subroutine to dispatch microservice instance into edge sets. By creating multiple access to services, our policy boasts a faster response for mobile devices. The SAARP not only take the uncertainty of microservice composition schemes into consideration, but also the heterogeneity of edge sets. That's my presentation. If you are interested in this paper and have questions, you can ask me or email me with your questions. I will answer your questions as best as I can. Thanks for your listening. Thank you.
Thanks, Zhao Hailiang, for your presentation. We do have time for questions. So would anybody like to ask questions?
Yeah, maybe I have one question.
Okay, go ahead.
Yeah, so thanks for this very nice presentation. Just for my understanding, so here you are considering the problem of placement, and you said that you are creating like new instances of the service, right?
Yes.
Okay, so there is the dual problem where you do it's a kind of scaling, right? So you can consider also adding resources to one service. Did you consider this, or this is not? I mean, you just consider the case where you are creating new services. Because like,
in this paper, we just consider a simple service function chain. It's a chain of microservices. We don't consider the complexity structure of the services.
Yeah, so you are creating a new instance of the service like anytime there is need, right?
Oh, yes, yes.
But you are not adding resources. So it's not a provisioning problem. So just I'm trying to understand, is it a provisioning problem that you try to add the resources to the service? It's kind of like vertical scaling, or you are anytime there is a need, you create a new instance of a service?
Because we have, in our assumptions, we have Docker images and the initialize of microservices. The time we just skip the time, because in this paper our mainly addressed is the routing time and the service execution time, and the initialize of the image is skipped in this paper. We may add this time into our formulation in the following works. Yes.
Okay, thank you. I have another question if there is something.
Yeah, I mean, I have a similar, a simple question. So you talked about latency here. How would your approach change if you had some other metrics? Say you were interested in throughput despite unreliability and so on.
Sorry, I just can't understand what you are asking.
So your metrics.
Can you repeat the problem again?
Yeah, I think you're talking about response time, but if you wanted to talk about number of transactions per second.
Our response time is the average of the response time achieved by every end users.
Right. But yeah, you're relying on a redundant approach, right? You said you have redundancy, and so you can take the fastest response.
Yes. The faster response I mentioned here is because we use edge computing. That means the candidates, the service candidates, microservice candidates, they are deployed on the small cells. which means we do not, or we haven't need to process to send our service request demand to the cloud data center. We don't have the backbone transmission here, so we can enable a faster response.
Right. I think you mentioned something about a redundant system. You said there was redundancy in your approach. Maybe not. I think it's okay. Jamal, do you want to ask your question?
Yeah, I have just one maybe quick question. So here, your approach, so you solve it using a kind of heuristic, right?
Yes.
So is it because the problem is non-convex? I mean, the optimization here. Just I'm trying to understand, I mean, where is the complexity of like minimizing the response time? Like, comes from where?
The first problem is we don't know the end user's service selection. Here we can go to here. For example, some user he chose the C11, C21, and the C31, C42 here. But actually in real cases, we don't know what he chooses, what he has chooses, because that's the uncertainty. The uncertainty increase the hardness of the problem. If we don't know what he chooses, how can we place the instances? Well, the instances are microservice instance, so we have to know the microservice he chooses. That's the first difficulty here. And the second difficulty is our formulations. As we have, as I had said before, we need to discuss many scenarios. The first scenario is because for example, the end user, his selection, his first microservice request is not processed by any SPS because no SPS is around him. So his request command has to be sent to the cloud through the macro base station. And there are many other cases we have to discuss. Here we just list the uplink transmission time here, but actually we have downlink transmission time, and the input and output data size, how they transferred. We need to use the shortest path algorithm and many other algorithms here. That's also increases the problem. When we implement it with the GA algorithm, we have to implement all these discussions in our code. So that's very difficult here. That's the second difficulty.
Okay, thank you.
Oh, thank you. If I had any questions, you may email me with your questions in detail, and I will answer you as best as I can. Thank you very much.
Okay, thanks for your presentation. Let's go to the next speaker. And could you hand over, Jamal, if you can hand over control to Masood?
I want to present our paper with the title of GDPR compliance for
Masood, I'm not getting a good audio. I'm not sure if other people are in a better place, but I could hear you well earlier. Could you adjust your microphone, please?
Sorry.
Yeah, now I can hear you, I think.
Yeah, can you hear me? Can you hear the videos?
No, we had problem here in the video.
Yeah, I think we assumed that you would give the presentation live, but So that's, if you can do that, that's the best thing.
When you share the screen, you have to share the whole window. Okay, good.
Okay, sorry.
We could not barely hear you. So are you using the recording?
Okay, yes. Yeah, I use the recording. Yeah.
Yeah, if you use recording, then you need to get off your headset.
Okay, okay. Just can you hear me now?
Yeah, we can hear you.
Okay,
So,
just I will go through that. Okay, this paper is about checking GDPR compliance for cloud-based services. Actually, the topics that I want to present today is about user privacy and GDPR, a blockchain-based solution, and a case study, which is a cloud-based pharmacy, and a conclusion. First, I start with user privacy and GDPR. Normally, many online applications currently receive personal data from their customers. And for example, we have a number of data breaches, look like British Airways, cyber attacks on hospital systems, and etc. So, and also we have the other data breaches in Marriott hotels and their subcontractors. And especially in the cloud ecosystems, normally users trust the cloud portal and provide the personal data through the portal. But in the backend, we will have a set of cloud services that can manipulate user data while the users are unaware of such providers and what operations will be operated on their personal data. So for enhancing data privacy, we have GDPR. This is the European legislation that affects on May 25, 2018. And it focuses on personal protection of personal data, and it enforces the actors or providers that process personal data to comply with the rules. In the main elements of GDPR are data subject, data controller, data processors, and data joint controllers. The data subject is user, which is identified via an identifier such as name, location. The data controller specifies the purpose of data processing, and data processor is responsible for processing personal data on behalf of the data controller. In case we have more than one controller, the notion of data joint controller is raised. So the main question is that how we can automatically verify GDPR rules over cloud-based systems. So in our solution, we track the audio trail of data processor and data controller. We want to show that how we can implement a smart contract for verifying GDPR, and we want to know what GDPR rules should be checked through such a smart contract. And we want to design an architecture for interacting the controller processors on users operations through smart contracts. And we want to check the blockchain and the content of blockchain and detects the GDPR violations. So in the solution, we first we classified the GDPR rules that we have for the operations that can be occurred by the cloud providers on personal data. We classified the operation as read, write, profiling, and transferring in general in this case. And we assigned the GDPR obligations that we have as some legal question to these operations. And then we translate these into some algorithm or through some pseudocodes to track, for example, how we can check the compliances regarding the operation. So in our solution, we have an architecture involving data subject, verifier, and actor that are communicating with the blockchain-based virtual machine like Ethereum. And in the Ethereum or public blockchain, we have a GDPR smart contract factory involving 4 different smart contracts: user consent, GDPR compliance contract, container contract, and verification contract. And the deployers of such contract will be organized through an agent which is called the contract activator. So for the GDPR compliance contract, actually it checks receive the purpose of data processing from the cloud providers and checks the GDPR compliance of data that received from the providers. And as its output is the GDPR status or GDPR compliance status of such providers for the users. And we have the user consent contract that assign a positive consent to the purpose of data processing. And the user freely through this contract can retrieve the content of purpose of data processing from the blockchain and get their consent to the providers, and we kept them inside the blockchain. In the container contract, we have a container on the cloud side that monitor the activity of cloud and run a smart contract which is called container and log the information or events which involves the operation of the provider on personal data in the blockchain. And finally, we have the verification contract that checks the identity of provider and check whether the providers do the operations that already got the consent from the user, and also process the personal data that already accepted by the users. So these types of verification will be done through a smart contract. So this slide shows the interactions or data flow between the smart contracts. In our contracts, that verification contract should call the user consent contract, GDPR complex and container contract to verify the GDPR violations. So, and this shows the protocol that we have for storing purpose of data processing inside the blockchain through the elements of data subject, contract activator, actor, and blockchain. First, the purpose of data processing will be stored through an actor inside the blockchain, and then the contract activator provides the address of blockchain to the data subject, and data subject can retrieve the content of blockchain and store the vote, I mean consent or rejection to the blockchain. And this is the protocol for sending the information into the blockchain through the containers. So first, when the actor launch a container on their side and they process personal data and log the some events which involve the operation that the data that is processed by the provider and the address of the actor or provider. And finally, we store this data to the blockchain and provide the user a function which is called attestation for tracking what happens by providers on their personal data. And this is the protocol for verification part that shows the, for example, we automatically propose a smart contract that checks the content of block and detect violations and report the contract activator about the results of the detected violations. And in the verification part, in our implementation, we checked the address of actors or providers, the operation that executed on the personal data, and the processed personal data that involved in the operations. So here is a scenario of a cloud pharmacy, which involves an online pharmacy service, payment service, and shipping service. In the online pharmacy, we can have a set of activities for getting the prescription from the patient or user and validate the invoices and store the data inside some local databases or health record and issue invoices and medicines for the patient. In the payment, we can have two modes, Western Union and PayPal organization for organizing the payments. And finally, in the shipping, we can send the medicine to the patient. So in this pharmacy, so we have a pharmacy service provider that asks name, address of electronic version of prescription and bank account details. We have a payment service provider that requires some personal data, including bank account details. And we have a shipping service provider that needs the destination address of customers for the aim of profiling. So here shows that the controller, the data controller and data processors can be online pharmacy. The data processor can be payment, and for shipping also is a data processor that because they request the personal data and they share the personal data among each other. So this slide shows the integration of blockchain or a smart contract inside the business process of online pharmacy. As you can see, we involve the GDPR compliance contract inside the online pharmacy. And this is also the integration of the smart contract and blockchain inside the submission files. It means that what happens through the container by activating the smart contract and running their functions. And also this slide shows the verification part that is done after the execution of or the life cycle of operations through the business process. So here are two of selected of our experiments that shows that our smart the transaction fees regarding by changing the number of actors and the operations and about the detection rate. It means that the percent of successful detection of violation. And also we have we evaluated the mining time by changing the number of actors and operations. So as a conclusion, we presented a blockchain-based abstract model for the verification of GDPR in cloud. And through our method, the GDPR obligations are translated into a set of outputs. And we propose several protocols and an architecture, including ratification, submission, and verification phases. And our smart contract were integrated into the cloud pharmacy as a case study. And we deployed our smart contract in blockchain test network and investigate their cost and mining time. Okay, thank you very much. If you have any question.
Okay, thanks, Masood, for your nice presentation. Let's open the floor for questions. Does anybody in the audience would like to ask something? Okay, if not, I can ask a couple of questions, and I think maybe Jamal, I'm sure, also has similar questions. So what makes the approach interesting from my perspective is that you're trying to model GDPR in a way that can be expressed as contracts that can be automatically processed. And so I wonder if you can elaborate on how those contracts are expressed. Like, what's the nature of the contract? Because GDPR has many clauses in it. The various articles that come into play. And are you focusing on some of them? I assume you are. Can you state which aspects of it you're addressing and how you're addressing them? Like, do you have an example or some way to make it sort of more real?
Thank you very much for your question. It's really, I think it's a good question. Actually, we evaluated the GDPR rules and GDPR articles that we have. Some of the rules cannot be programmed, but the others can be programmed as set of, for example, if and else conditions. For example, we evaluated the rules that we have for data access, for data storage, for also data profiling, and for the data transfer rules. because we know that which conditions involved. For example, for the data transfer, for example, the companies should be involved in the European countries destination, and the encryption of data should be guaranteed through the companies. So we can easily track that by, for example, if and else conditions, or for profiling, the age of customer is important. That should be adult, for example. So we can easily also check through the smart contracts. So this is why that we involve that. And also regarding the user consent, so we also supported these rules by implementing, for example, purpose of data processing already should be stored in the blockchain, and then the user should give the consent, and this consent should be stored also in the blockchain as an immutable evidences. So it means that such rules can be also, for example, translated through the smart contracts. But the system is under development with more operations and with more GDPR legislation that we can assign to these operations.
Okay, thank you. I have another question. This is about the business process, that BPMN diagram that you showed.
Yeah.
So, yeah, go ahead.
Sorry, because the question is that how we can integrate our solution, I mean the blockchain and running the smart contract in the business process of the real applications. For example, this is why that we choose a cloud-based pharmacy scenario, the business process of a cloud-based pharmacy, and we involve for the test or a smart contract inside the business process.
Because I wonder, the reason I brought it up is that I think this BPMN style modeling is particularly it's rigid. I mean, it doesn't explain, it doesn't provide the flexibility that you could easily provide through, for example, through blockchain. So maybe you should, if you had considered alternative representations, then you'd be able to achieve greater flexibility in your model. So maybe this, your implementation will be better. But maybe some of those things I think we can communicate offline as well about that.
Yeah, surely, because we propose also the architect there and also set up protocols to be generalized or approached, but I fully agree.
Okay, I think Jamal may have.
Yeah, if there is time, so just one question. Yes, well, thanks, Masoud, for the presentation. Very nice. Just one thing, I mean, here, when you use smart contracts, and I saw that you are doing some verification and you have some inputs to those smart contracts.
Sure.
So how do you get those inputs? So they are outside the blockchain, right?
Actually, for example, we have different blockchains, networks. First, for example, we got the user consents and we put inside the blockchain. And we have another smart contract through the container that log what happens inside the system and put this in the blockchain in the execution time. And the verification contract just call the previous smart contract, I mean the user consent and the submission contract, I mean container contract, to see what happens inside the system. For example, if a provider does an operations on the personal data, but they didn't get already the user consent, it is detected through the verification contract as a violation.
But are you calling some oracles or?
Actually, I used Ethereum and through the Solidity language, I, for example, I define the smart contracts and I call the smart contract structures that we want to check for the verification. It means that the input of the verification contract are the block contents that is stored through the user consent and container contracts in my
so you are not getting any data from the oracle from outside the block.
No.
Everything you assume it's already in the block.
They are on chain, yes. So, yeah, they are on chain. They are not off chain.
Everything is on chain. So it's but did you consider that it's maybe heavy? So because usually we can use an oracle and then you can get the data to the contract, to the smart contract.
Yeah, I fully agree. But we use the Ethereum blockchain, and we just went through the on-chain protocols.
Okay. Okay, thank you.
You're welcome. And sorry just for the presentation, because I already assumed that it is on the record, and I wasn't. Okay, sorry.
Yeah, no problem at all. I think it's all, these online conferences are new to all of us. So we're learning as we go. I assume there are no more questions because nobody spoke up. So if that's the case, I think there's no more of an agenda. So we'll just declare this session closed, and I hope you'll attend the remaining J1C2 sessions that are coming up. All right. Thanks, everyone.
Okay.
Okay, thank you.
Bye bye,
Yeah.
everyone.
See you later.